we talked about z-test. We use z-tests when we have the population standard deviation. If we don't have the population standard deviation, then we have to approximate it by using the sample. When that happens, we're going to use a t-test. So a one-sample t-test asks the same types of questions. Is the sample mean equal to a given mean? In this case, we have both the sample mean and the standard mean to use to calculate our value. Now the assumptions of these t-tests is that our data are random and independent, and we'll assume this assumption for all of our tests. And our second assumption is that our sample data are normally distributed. We'll return to these a little bit later. Now just like a z-test, we're going to do this conversion. We're going to take our sample mean minus mu, and then we're going to divide it by the standard error, where we use the sample standard deviation and the square root of our sample size. But unlike a z-test, when we apply this transformation, it now approximates a t that follows a t distribution with n minus 1 degrees of freedom. Recall, we've already introduced this t distribution when we calculated a 95% confidence interval. With that confidence interval, we multiplied our t by the standard error to figure out the plus or minus part of that confidence interval. So same type of principle. With that standard error, we're using our sample. The p-value is the area under the curve, under that t-distribution curve. What we're looking at is the tail, because our interest is this mean equal to a hypothesized mean? Our p-value is the probability of getting data as extreme or more extreme. So when we get this, we're looking for all of the area to the right or to the left of our t. Now why do I say right or left? It's because we can have a negative value depending on which of these is larger. If x bar is larger, then we're going to go to the right of our t value, so the upper tail. If this x bar is smaller, then we're going to go to the left of our t observed value, which is the left tail. So when we do this by hand, what we're going to do is calculate our t observed value, so do this transformation, get our t observed, and then we will compare it to a value in our t table. Now the value that we obtain is basically going to be the same values that we would use for a 95% confidence interval. If the absolute value of our t observed value is greater than or equal to the critical value, then we know that the probability, our p-value, will be less than or equal to our alpha level that we set. So either 0.0, it'll typically be 0.05. If the absolute value is less than the t critical, then we know our p-value is going to be greater than that 0.05 value. So let's go through an example. Average size of species A is 89.44. In a sample of 10 individuals, you calculated a mean size of 92.99 and a standard deviation of 5.11. Is our sample similar to species A? So note from this question, we have a given value, 89.44, and then we have a sample. We have a sample of 10 individuals, we have a mean size of 92.99, and we have a sample standard deviation of 5.11. So we're comparing a mean, 92.99, to a population mean, 89.44. That should tell you that we are doing either a z-test or a t-test. But since we have a sample standard deviation, that tells us we're definitely doing a t-test. So our p-value is always the probability of getting data as extreme or more extreme. Well, 92.99 is greater than 89, so we're going to be interested in the probability that we could get a value that's greater than or equal to this value, 92.99. Now I multiply it by 2 because this is a two-tail test. Can you see why? Hopefully you said it's because our question is just asking, is our sample similar to species A? It doesn't set directions, it just asks, is it equal or is it not equal? So we didn't say, is the sample larger or is the sample smaller? We just said, is it equal? So when we run our test, we have to account for the fact that it could be larger or it could be smaller. So we run a two-tailed test. Now with our t, the t distribution is symmetric around 0. So all that we have to do is calculate one tail and then multiply by 2 to get the proper p-value for this t-test. So if we're looking for lists, we do our same transformation that we did for the z. So we're going to take our x minus the mean divided by the standard error. Note I use the sample standard deviation and then the sample size of our sample. I do it same on the right hand side, and I get a t. The area that we're looking for is part of that t distribution that's greater than or equal to 2.197. Now we can calculate this in R, and I'll show you how. But we're going to use our table. So pause the video, open up your table, and come back. Alright, so hopefully you have your t-table, and here's mine. We are looking for the t-critical value. So the critical value is the cutoff value. It's that value that marks 5% in our tails. Well, that means, since we're doing a two-tailed test, we want 5% in both tails, which corresponds to this 0.05 column. So we're going to use this 0.05 column for a two-tailed test. What we then do is go down to the appropriate degrees of freedom. Now our sample size was 10. Our degrees of freedom for this test is the sample size minus 1. So our t-critical value is 2.262. We then compare our t-observed value, which we calculate as 2.197, and we're comparing it to this 2.262. Because our t-observed value, the absolute value of this t-observed, is less than 2.262, we will fail to reject our null hypothesis, which means our p-value is greater than 0.05. If our t-observed was greater than that t-critical value, then it means we're in the shaded region, which represents 5%. So we would know then that our p-value was less than 0.05. In this example, our p-value is greater than 0.05, so we fail to reject our null hypothesis. Now remember, our null hypothesis is that our means are equal. Our sample mean equals our population mean. So if that's our null hypothesis and we fail to reject it, then we would conclude that our sample is equal to that population mean. So our write-up goes back to those 5 things that we have to report. We have to report the conclusion or the interpretation, the test statistic, the degrees of freedom, and the p-value. In this case, we basically have all 5. So we write our sample of specimens appears to be species A. Why did I write this? Well, because it goes back to our question. Is the sample similar to species A? That's our biological question. That's what we're trying to answer. That's the interpretation. That's our conclusion. So our sample of specimens appears to be species A. We ran a t-test. Our t-statistic, our t-observed, is 2.197. That's what we calculated. Degrees of freedom is 9. P-value, I listed as 0.06. Now I did this because I know what the p-value is from R, but we could also kind of get a better approximation. We know it's greater than 0.05 because our value was less than that, was less than our t-critical value. What we could do is compare our observed value to the values in this row. Because our value falls between these two values, the 1.833 and the 2.262, I know that my p-value is going to be between the 0.05 and 0.1. So if I really wanted to be a little bit more specific, I could be p is less than 0.1, and this assumes we don't have R to calculate the actual p-value. We could say p is less than 0.1, and that works. Or we can say p is between these two values. I think it's just okay that if we have a non-significant test, that we could say p is greater than 0.05. I'll be happy with that. So I said I had the p-value in R. How do I do this? Well, I'm going to use the pt function. We've used a p function before. We used p-norm to calculate the area under the curve. PT works the same way, but this time we're calculating the area under the curve for the t-distribution, hence the PT. So to use this function, we use PT, we give it the t-observed statistic, the one that we have to calculate. We specify the degrees of freedom, which remember is our sample size minus 1, and we specify lower dot tail. So lower dot tail is either going to be true or false. If you can remember this, you'll be okay. So if the t observed that you calculate is negative, then you will use lower dot tail equals t. If the t observed is a positive value, then use lower dot tail equals false. So if it's negative, we're going to the left of that value. If it's positive, we're going to the right of the value. Now this is for a one-tailed test. If we wanted a two-tailed test, we use the same function, but multiply by 2. Why multiply by 2? Because our t-distribution is symmetric. So for our value, we calculated 2.197. That's our t observed. We had to calculate it. We're going to pass that to our PT function, specify our degrees of freedom equals 9, and lower dot tail equals false because this value was a positive value. And then we multiply by 2 because this is a two-tailed test, and I get a p-value of 0.0556. So our p-value that we report would be 0.06. Remember, p-value and our rounding rules. That was in an earlier presentation. If we have a p-value that's greater than 0.05, we just round to 2 decimal places. Alright, so let's do 2 practice problems. Practice 1, for both of these practice problems, we're going to do it by hand. We're going to determine if we're going to accept or reject our hypothesis and have a write-up. And then what we will do is calculate the actual p-value using R. You will have to know how to do it by hand and using R for exams. So for practice number 1, here's our problem. Last year, the average number of tomatoes produced per plant was 54. This year, the plants averaged 48 tomatoes. Was this year's crop worse than last year's crop? So in this problem, I give you your sample size, your average, and the sample variance. I want you to use a t-test to answer this question. As you practice, write out the hypotheses, so our null and alternate hypotheses, calculate a p-value, or when you do it by hand, an approximate p-value, which means less than 0.05 or greater than 0.05, and do a write-up. And then once you finish that, check your work in R by calculating the p-value. Pause this video, work on problem 1, and then we'll work through it. So let's work this problem by hand. I've written out what was given in the problem. We have a population mean of 54. We have a sample size of 8. Our sample average is 48, and our variance is 9. Our standard deviation is the square root of the variance, so the standard deviation is a 3. Now ask, is our sample average smaller than the population mean? So was our average worse than last year's average? Because I have this S, this variance or standard deviation, we're going to run a t-test. So with a t-test, our null hypothesis is always that our sample average is equal to our population mean. Our alternate is given by the problem. In this problem, I asked if our sample average was less than that population mean. This tells me that I'm going to run a one-tail test. So for a one-tail test, we still want an alpha level of 0.05, but this time we want all of that 0.05 in one tail, not divided among both tails. We want all of that 5% to be in a single tail. So our p-value is the probability that we would get data as extreme or more extreme than what we observed if our null hypothesis is true. In this case, we want to know the probability that we would get a sample average that's less than or equal to 48. So I'm going to do our conversion. So subtract population mean divided by our standard error of the sample using our sample standard deviation. And when we do this, instead of a z, I get a t. So I am looking for the probability that we would get a t that's less than or equal to negative 5.657 if our sample mean was actually equal to that population mean. Now I don't multiply by 2 because this is a one-tail test. We're looking at only one tail. So at this point, our t observed value is negative 5.657. We would use this to calculate an actual p-value in R. When we do it by hand, we're going to compare this value to our t critical. Our degrees of freedom in this case is our sample size minus 1, or in this case, 7. And our t critical value is pulled from our t-table, and it's 1.895. I will note here that I did not use the 0.05 column because the 0.05 column has 5% of our values distributed among both tails. We want 5% to be divided among one tail, so we're going to use the 0.1 column, and we will always use the 0.1 column whenever we run a one-tail test. So for all one-tail test. Alright, so we have our t observed, we have our t critical. What we do is take a look at the absolute value of our t observed. In this case, the absolute value of our t observed value is greater than our t critical value. Therefore, we are going to reject our null hypothesis. It is too unlikely to get a t-value as extreme or more extreme, or I should say, to get a t-value this extreme just by chance alone. So we're going to reject our null hypothesis and conclude that our sample mean is worse or less than mu. And if we need a p-value, we know our p-value is going to be less than 0.05. And I know, based on how far away we are from t-critical, that we're actually going to be much less than 0.05. So now we have our t-test by hand. Let's utilize our t-observed value to calculate the actual p-value in R. So we did it by hand. Let's calculate p-value in R. So our hypothesis for one sample test is that our sample mean is equal to our population mean, and our alternate is that our sample mean is less than the population mean. So we're doing a one-tail test. We can calculate our t observed. We already know it's negative 5.657, or if we go out a few more decimal places, that's our value. What I like to do is calculate the t observed in R and then save it as t obs, or t observed. So note, I didn't use 3, I used the square root of our variance over the sample size. It's because our square root can distribute to the numerator and the denominator. It's just one less step I have to do. And then once I have t observed, I use the pt function, pt of t obs, df equals 7, lower dot tail equals t, where t, because this is a negative number, and it returns our p-value. So in this case, p-value is 0.0004, or rounded at least. So our write-up is this year's crop of tomatoes was worse than last year's crop. Again, we're referring back to the biological question. T-test, our t observed is negative 5.66. We typically round to 2 decimal places for the test statistic, and this time I gave the degrees of freedom as a subscript. So t subscript 7, and then I report the p-value. So just recall the reporting requirements. We need all 5 for a t-test. So now we did practice 1, try to do practice 2. Again, do it by hand first, and then calculate p-value in R. So I set up this problem same way as I did last problem. I write out what was given. So we know our population mu is 82.5. That's what we're comparing to. Our sample has 12 samples. In that sample, we have a sample mean of 79.3 and a standard deviation of 1.6. Our question is average lake temperature similar to that of Lake Nasworthy? So is x bar equal to mu? Well, as with any test, we always assume that our sample came from the same population, which means our null hypothesis is that our sample mean equals our population mean. Since we have our sample standard deviation, we know we will run a t-test. Our alternate hypothesis is that our sample mean is not equal to mu. So we didn't specify direction in the problem, so we don't do so with the alternate. So this tells us that we are going to run a two-tail test. So as before, we want a probability that we get data as extreme or more extreme just by chance alone if our sample actually did come from our population. So we want to know the probability that we would get a sample mean less than or equal to 79.3. This is a two-tail test, so we would multiply our p-value by 2. We then convert our value to a t by subtracting our population mean and dividing by the standard error. So divide by 1.6 divided by the square root of 12. And we do that to both sides. And we get 2 times the probability that we would get a t that's less than or equal to negative 6.928. So if we were doing it in R, we have our value that we can pass right to the pt function, but we're doing it by hand, so our t observed is negative 6.928. The degrees of freedom for this test is our sample size minus 1, or 11, and our t critical value gets pulled from our table, and I get 2.201. This is a 0.05 column, and it's a 0.05 column because we're doing a two-tail test. So looking at our data, absolute value, or our t values, absolute value of our t observed is greater than our t critical value. So therefore, we conclude that our sample mean is not equal to our population mean. So let's do this in R. Again, this is a two-tail test, so our null hypothesis is that our means are equal. Our alternate is that the means are not equal. So just like before, I'm going to calculate t obs, so t observed value. I'm going to do it in R and save it as t obs. This value is 6.928203. I'm going to pass that value to the 2pt function. This time we multiply this by 2 because we're doing a two-tail test. I use lower dot tail equals t, again, because this is a negative value. If it was a positive, we'd use lower dot tail equals false, but this is a negative value, and this will give us our p-value, and it's a really small p-value. So our write-up in this case, again, our write-up always refers back to our question in the problem. So our conclusion interpretation is that average lake temperature of Lake Texoma is not similar to that for Lake Nasworthy, so they're not equal. We ran a t-test. T is negative 6.93, degrees of freedom is 11, and p-value is less than 0.0001. We had a really small value, so I cap how small I write the p-value by writing less than 0.0001. I do put a box here about reporting degrees of freedom. We have two options. We can write degrees of freedom as a subscript, which is what I normally do, or we can write df equals the number in the text. Both ways are suitable. If you do it this way, which you'll probably do it on a markdown document, that's perfectly fine. We just want to make sure that we do include all 5 things that we have to report. So the summary for the one sample t-test. We use it to determine if our sample mean equals a given mean. And when we're testing this, we have both the sample mean and the sample standard deviation. Our assumptions of this test is that data are random and independent, and our data are normally distributed. Now we can't test this when we do it by hand, so the problems will state something like assume all assumptions are met or assume data are normally distributed. When we work with vectors, we'll check this assumption. How do we actually use the test? Well, we're going to calculate our t observed, and then we're going to compare our t observed to a t critical value that's pulled from the t table. That's when we do it by hand on, let's say, in pen and paper. If we use R, we still have to calculate t observed, but this time we use the pt function to actually calculate the p-value. When we report this test, we're going to report the conclusion, the test statistic, degrees of freedom, and the p-value. And note, with the degrees of freedom, you can write it as a subscript with part of the test statistic, or you can write it as part of the entry in our parentheses. So this wraps up the z-test and the t-test doing it by hand. What normally happens, though, is that you collect your own data, so you have the vector of data that you can then import into R. And I ask, if you already have the vector, why would you even bother doing a t-test by hand? Well, you wouldn't. You'd actually use R to run a t-test, and that's what we will learn how to do next.